So, what is the state space of the n queens problem? It is essentially the number of different positions of those queens in their n by n board. From combinatorial math, this is the number of possible selections of k elements taken from a set of n. In our example, n is the capital N by n, while k is the capital N. For instance, for n equals 8, the state space is approximately 4.4 times 10 power to the 9, or 4,000 million different ways in which you can place the queens on the board. The number of solutions, however, is much smaller. This table shows a relation between the size of the board and the solutions available. There are two rows, fundamental and all. Let's focus on the all column for now, which indicates how many solutions exist. You can see that for n equals 1, there is only one solution. This is one single cell and one queen on it. Pretty simple. For n equals 2 and n equals 3, there are no valid solutions, as all positions in which you can place 2 and 3 queens respectively result in at least one queen threatening another. As the size of the board side increases, the number of solutions grow, reaching very high numbers. The fundamental row describes how many of these solutions are unique, instead of being reflections of another. In this problem, you can augment the number of solutions you find by mirroring one valid solution either horizontally, vertically, or diagonally. In these cases, the positions of the queens are technically different, although the solutions are tightly related. We are moving into tree search now. So tree search is a category of search methods that use a tree structure to navigate through solutions. On these trees, each node is a possible solution to the problem, and the root is the solution used to start search. Each link to one node to a child is a movement in the search space. This can be, for instance, making a change in one candidate solution. Or, when talking about games, these are actions that players play on them. For instance, imagine we are playing the game of tic-tac-toe, where the objective is to win by setting 3 of your symbols in a row, 2 players playing simultaneously. We are moving into tree search now. Tree search is a category of search methods that use a tree structure to navigate through solutions. On these trees, each node is a possible solution to the problem, and the root is the solution used to start the search. Each link to one node to a child is a movement in the search space. This can be, for instance, making a change in one candidate solution. Or, when talking about games, these are actions that players play on them. For instance, imagine we are playing the game of tic-tac-toe, where the objective is to win by setting 3 of your symbols in a row, 2 players playing alternatively. The root node in the tree on the right is an intermediate game state, in which the circle player must make a move. The second level of the tree represents all positions, 4 of them, where a new circle can be placed. This is quite common. Normally, more than one action can be taken from each state, and in some cases there are different routes that lead to the same state in the future. This is the typical structure of a game tree, which contains terminal nodes, representing endgame states, either winning or losing states, and non-terminal ones, where more moves can be made. What are we searching in this case? A solution that results in a win for the moving player. And once we found it, we just need to take the actions that we think will lead to that victory. Different tree search algorithms differ on the way these trees are navigated, and which actions are explored first. To show how some of these algorithms work, we are going to use now the 8 puzzle. This is a single-player game where the objective is to sort a series of numbers from 1 to 8 in a 3x3 board. One cell is empty, which should be left on the bottom right corner. Each action consists of shifting the empty cell either up, right, down, or left, and the puzzle might start in any random position. In the example shown here, the empty cell in the middle is shifted to the right, moving the tile with the 7 to the center of the board. Here we can see the game tree for the 8 puzzle, with a possible starting board position in the root. The second level of the tree represents the 4 states reachable after one move. Subsequent moves modify further the board. As you can see, when the empty cell is next to an edge, the number of possible moves is reduced to 3, so the number of available actions on each state might vary. This game tree is of course incomplete. You could be adding more and more nodes to the tree by inserting more actions from each state. Some of those nodes will be terminal, as they represent a board configuration that matches the goal state. You can see the tree as a vast space of board configurations where some of them are the goal we are looking for. Our tree search algorithm is going to determine how we navigate this tree to find a goal and solve the puzzle. Under uninformed search, which we can also call blind search, the algorithms look for a goal without any information about it. It does know how a goal looks like, but it does not have an indication or use any function to determine which actions move the state closer to this goal. They are brute force algorithms that navigate the tree blindly looking for a goal. These are among the most basic approaches that can ever be used, and many of them exist. We are going to see the following methods. The first algorithm we are seeing is breadth first search, or BFS. This method is very simple. It explores all actions available from a node before going deeper into the tree. So, in this case, we will only reach the tree depth D once we've visited all nodes in depth D-1. In this figure, nodes will be explored in the order of the red arrow.